Hello everyone, welcome to this session, a GPU native approach on tackling grid topology optimization. My name is Christian, I'm working for Elia Group.
And I'm Nico, working for InstaDeep and effectively for Elia Group.
And what can you expect during the next around 25 minutes? So on the one hand, we'll discuss a bit where we come from, how this started. Then we will tackle two main approaches. On the one hand, fast load flow calculation, especially on DC. Then we will look on the optimization, how we tackle this. We have a look at the current results and our roadmap. And then if you have questions, don't hesitate. Feel free to ask. If you have questions in the meantime, they're short, just raise your hand, we'll be happy to answer. I think this I will keep quite short. We are Elia Group, we are the TSO of East Germany, so 50 Hertz, and of the Belgium. And therefore we are two TSO that we are operating two different grids. They have a bit different requirements, but for both of them, topology optimization is quite relevant.
And what's InstaDeep? Basically a decision-making AI company. You can see it as the little brother of DeepMind. We've been growing steadily for since the 10 years we exist and tackle various high-profile, very difficult challenges. Among them, grid topology optimization. Also keeping it short now.
All right, so why is topology optimization, or in general, this interesting? Some of you might know the numbers from redispatch volume, or in general, grid congestion in Germany. We have quite high problems, around 4 billions in 22, 3 billions in 23 on redispatch cost. That's quite a huge number. Also, the amount of curtailed renewables that we have. Wind offshore, I think it was last year around 25% that was curtailed. So there are various reasons why we need to tackle redispatch, or how we can potentially deal with grid congestion and reduce it. What are two solutions in the short term, at least? I mean, there are other solutions in the long term, like, for example, hello. Yes. Yes, sure. You're welcome. So, of course, in the long term, there are other solutions to this, but in the short term, you have two main areas on how you can solve grid congestion. On the one hand, redispatch. So this means that when you have a power plant somewhere in a congested area, you try to reduce the infeed of it, and therefore in another area, you increase the power plant generation, which in the end leads to the one that you have to pay the one that is decreasing, and you also have to pay one that is increasing. So that's a quite costly measure, but it's done quite often. And then on the other hand is topology optimization, which is just about reconfiguring the lines. So if you can think a bit about, if you take an analogy, for example, when you're in a traffic jam, with Google Maps sometimes proposes you in a way to kind of go around. That's a bit what we do with grid operations and topology. It's a bit not exactly the same, but just to try to make a picture to it. The issue with just this is it is really difficult to find. What are topological actions that we consider? And there are three main ones. So here we have substation, or actually two bus bars. There's one that is considered bus bar splitting. So we kind of separate the two bus bars itself. So for example, by opening a bus bar coupler, either here or potentially also in here between. We can do bus bar reassignment. So kind of injection and load, we kind of change to which of these bus bars they're assigned to. And then you can, of course, also switch off, switch on a certain line. So basically, these are the three topological actions that we look at. And if you combine all of them, you have a quite high number, 10 to the 120 of combination that are possible. And these, like the combination, all of them are quite difficult to linearize. Which brings us to the next slide, is how you can potentially solve topology optimization. On the one hand, you can try to linearize and simplify, but as to our knowledge, for these three together, there is no linearization possible. And then there's the other way that you can try to search. So actually just try all of them. But as we have seen, 10 to the 120 possibilities, it's quite a huge action space. So what do you need to do first? Well, you need to accelerate your whole environment to at least tackle, to a certain extent, the huge action space. And this is basically what we did. So one of on this project was first to accelerate the environment with fast load flow solvers, and then a next step to then start with a simple search and then advance on this. And with this, I pass to Nico.
And I will take you on a journey into the myths of the DC load flow math. And it's actually a wonderful world, the DC load flow math. I think it's way underappreciated what nice things you can do. So first looking at load flows in general. The load flow, the idea of a load flow is basically to answer the question, given an injection and a topology, what will be my flows on the grid? Where will the electricity go? Unfortunately, we don't know unless we computed Kirchhoff's and Ohm's laws. So that's basically the idea behind the load flow equations. There's just Kirchhoff's laws. You can compute the full equations. That's called the AC load flow. That's currently one of the best approximations of what's actually happening on the grid, the steady state load flow at least. Then there was the idea of, okay, we might have some scenarios where we can trade a little bit. We can trade some precision for computation speed. And the DC load flow computation was invented. The naming is a little bit misleading because it's actually a linearization of the AC load flows. Just the math looks just like DC, but it's actually still AC load flow computations. They are just called DC. Don't ask me why. So for this project, the choice was made to go into the fast world with the sacrifice of precision. Because, instead of linearizing, we want to brute force a little bit. And DC is a very good candidate for this. And DC has an interesting concept. So in itself, the DC load flow equation is a system of linear equations. I already said it's a linearization. So we have a system of linear equations. And this is a very common thing to solve. You just use like scipy.solve, and it solves a system of linear equations. Now, this is very suitable if you need one load flow, but we don't need one, we need a lot. And the idea back in the day was to invert this A matrix once, basically, and call it PTDF. And then you can solve a lot of load flows with similarities in it. And depending on how similar, there are various ideas around this. So there were people coming up with, hey, if you take a line out, you could define an LODF, which is a very small change in the grid. So effectively, this is a Woodbury rank 1 update to this inverted matrix, this PTDF matrix. Or you can actually close a line, again, a very small change in the grid. And you can keep going there, you can set phase shifters, and you can split buses. And I want to do a small raise of hands. Who of you heard of PTDF before he entered that room? Okay. Who heard of LODF before he entered that room? And BSDF? I told you before. So bus split distribution factors. This is actually a key component. This has been invented 2023, so a year and a bit ago. People at Tenet, credits to Joost van Dijk and Jan Fiban and co, came up with the math how to do the similar idea like the LODF. Basically, the LODF is you remove a line and apply this to couplers. And a coupler you could see as a line with infinite admittance. Now removing something with infinite admittance makes you divide by 0, so it's a little bit tricky to actually do that. But the math eventually came out, and you can do a rank 1 update with the BSDF. And this was a very key point actually for us, because if you look at it, the LODF, it's transmission line switching, and the BSDF is busbar reassignment and opening of busbar couplers. So suddenly we have the complete topology action space as very simple operations, as rank 1 updates to an inverted matrix. So you go ahead, invert a big matrix once. It's actually a 400 MB matrix, so it's quite a beast. But you have that, and then on that you can basically compute everything with rank 1. Rank 1 updates means you do matrix multiplications in the end. So quite a cheap operation compared to reinverting a system of linear equations. And that was the point in our project where we realized, yeah, we just basically do matrix multiplication. So we had and went to GPUs. GPUs are currently very much used in AI. AI isn't just matrix multiplications. A neural network is just a matrix multiplications, and then you, I don't know, you do a ReLU on it, and then another matrix multiplication. So GPUs are very good at this. In fact, they are so good that for us, we had a very significant speed up. So we developed a load flow solver which can do DC load flows using this BSDF, LODF ideas, and by now we also implemented PSDFs and MODFs and all sorts of other DFs. And we went from 100 load flows per second in Pandapower. So Pandapower is a grid modeling software. Some of you might know it. If you do use run DCPP, you can do that 100 times per second. Well, it's already quite a lot of load flows. Just taking the BSDF idea, and this is log scale, by the way. So who doesn't know log scales? That's a lot. Huh? So just taking the BSDF idea got us like in the tens of million load flows per second. Under changing topology. So this is basically different topologies that we could evaluate. And then we took that onto GPUs, and we actually breached the billion load flows per second. And this isn't on a like case 14 grid. This is the ActiveSG 2000, like also known as the Texas grid, a synthetic grid which is roughly resembling like TSO conditions. And this is 7 orders of magnitude. To you who don't know what an order of magnitude is, 1 is factor 10, so like factor 10 millions. Not only we are faster, we are also way cheaper. Shout out to the T4 GPU. Very slow, but super cheap. Like 5 orders of magnitude cheaper to compute load flows. Meaning we have a whole new world at our hand. And for those of you, like the grid planners in the room, the question might be, can I use this? Probably come to us after the talk. Now what do you do? Suddenly you have 1 billion load flows per second. You need to do something with 1 billion load flows per second. And what do? We built a pipeline. We took grid data, originally from Pandapower. Now we can also load PowSyBl. And then we feed it into a loop. I will explain a little bit what a genetic algorithm is in a second. But basically, we have an optimization loop. You can call it as a brute force search. It's a little smarter than brute force, but not a lot smarter. And in the end, we validate everything on AC to make sure that the assumptions which we did, like DC is a linearization, so we make an error in our load flow computations, that it's actually still holding, so that in the end we see, okay, whatever we computed on DC, it's not really worth anything unless we know it still works in AC. Okay, I promised to explain a little bit what a genetic algorithm is. It's inspired by biology, so you call everything like the individuals in the population, but eventually you just have a set of topologies. You change them, so you change a little bit here and there, or you cross them over, you merge them. And then you evaluate your new changes. And out of the set of topologies, out of your population, the worst ones die. And you keep doing that until you don't find anything better. There's not really a point of convergence. You just do that until you, I don't know, don't have time anymore, for example. Or you found something which looks reasonably sensible. And the trick is we used QDEX, which is a GPU-based library to do this fun. So we stay on GPU. We never leave the GPU. Like our critical optimization loop never leaves the GPU. And that's a very important part because the GPUs are very fast, but they have a PCI Express, which connects them to the rest of the world. And this PCI Express bus is super slow. So you want to avoid using that whenever you can. And staying completely on the GPU actually made it so we can optimize the 2,000 busbar networks, 24 time steps in 50 minutes. To a reasonable point. I mean, we don't know if it's fully optimized. There's probably no such thing as a global optimum in 10 to the 120 combinations. But at least it's good enough. It doesn't increase anymore. It looks like reasonably good. But what do I mean with reasonably good? So we did a planning on a benchmark on grid planning data. Grid planning data is very benevolent when it comes to loading and saving. They actually do a lot of studies, so you can easily get a grid file which is loadable in Pandapower and has like the same amount of elements in every time step and comfortable things like that. So that was something which we did back in January. A small caveat with that, grid planning data, though it's made to look as realistic as possible, it's still a synthetic benchmark, so the numbers, they don't really generalize perfectly, but it gives at least an idea where we're going. So the grid planners, they use integral, not grid-cal, unfortunately. But we pulled that out to Pandapower, then did an optimization run. And the results actually looked pretty nice. So we were able to shave off between like 30 and 50% in different time steps. We look at overloads here. And yeah, that was run within 15 minutes. So that was the first success, meaning it got us a ticket towards industrialization. Industrial reality is a bit difficult though. We have different formats, so we actually increased a little bit the support of grid modeling software. For example, in 50 Hertz, a lot runs on UCTE standard, which is, like if you hate CGMS, you will start to love it once you use UCTE. So UCTE is a really good standard for making you love other file standards. In the Elia grid, we can get with the converter through to power from Power Factory to Pandapower. So finally, we have the data for both the grids which are relevant to us, and we can get it to the optimizer. And yeah, Excel is not a database, but the reality is, like right now, we just display our results in Excel. So we are at the least fancy solution. Our goal is really to get topologies that are switchable. So to focus on the gritty things first, on the substance, and then we build something fancy looking around it later. Who needs that anyways? And the idea how we go about this, unfortunately, nobody really wrote down which constraints are there for topology optimization. There are some people who have like a rough idea. You can read something in this and that book, but there's not like a clear this can be done, this cannot be done, because the reality is no TSO has a really like holistic topology optimizer in production. There are some which can like select from a set of topologies, or but at least the operational reality in our TSOs at least is it's a manual process. So the operators, they know their constraints, they know in their head what they can do, what they can't do. But yeah, why write that down even, huh? So we started with a way too aggressive optimizer, like for example, we numbered them iteration 4. We had like 50% of overload reduction. I looked really great, and we were like, oh, we're saving the world. And then the operators were like, yeah, that's a very aggressive topology. That'll very likely crash the grid. So we added constraints, and we will keep adding that until finally we have a topology that's accepted by the operators, and it's an iterative procedure. We're finding out about new constraints every now and then. But yeah, our hope is basically to get this done until the end of the year. We will see if we actually, but that's the hope. Yes?
How do you integrate the constraints in the model? How do you take that into account?
Yeah, the good thing is we have this thing here. It's called the evaluation of each individual. Right now, that's a load flow computation. So we do a full n-1 analysis for every topology, meaning we can actually compute quite a lot on that topology. We can see what are the load flows. We can see what are the differences, how does it look like, and then we introduce penalties. So for example, one of the constraints that we found out about is that there's actually a certain number of opened couplers in the grid. If you have more than 15, it's actually operationally forbidden to do that, but if you have more than 5, the operators get nervous. So at the point here, we can put hard constraints that just within the mutation and reproduction, we can never end up with an individual that has more than 5 splits, for example, 5 open couplers. And then we can also add soft constraints. So let's say if we find a topology with 4 open splits, which is just marginally better than the one with 5 open couplers, then we would probably take the one with 4. So it's a mixture of penalties and hard constraints. We can implement both. The good thing is we don't really need to like linearize anything. We can just compute them and then penalize them. This is a gradient-free optimization. Basically no feedback involved. So we just, like if there's something wrong with our topology, we just code it in and solve that. Yeah?
Maybe also from this loop, do you test somehow for how sensitive, or like what if the load of generation shifts slightly with your topology still holds, or sensitivities? Do you check for that during this kind of?
So question was, do we check for sensitivities with the example of if load or generation changed slightly, do the topologies still hold? No, actually not. It's just like we do not compute any sensitivities. We evaluate load flow computations. So what we do is to have a certain error band. We put a conservative limit. So let's say if we would load a line up to 99%, there's a very high chance that under changing load and generation, we would violate something, that we would get a new congestion. So what we do is we make sure that we have a more conservative burden. We optimize like below 100%, sometimes to 95, sometimes to 90, depending a little bit on what we look at. So yeah, it's a sensitivity-free approach, meaning also, yeah, we can't really say why the optimizer is doing what it's doing. But in the end, we can prove on the load flow computations whether it's a good or a bad topology. So we actually do a full analysis every time.
Sorry, another question.
Yes?
Just, you know the initial population is random, right?
Yeah.
Why, in order maybe to be more realistic and to be in a more realistic situation, you could generate a population that is past situation of the grid. And in that way, you could avoid to have those crazy, and maybe having less constraints to input manually.
Okay, there were 2 points in this. Let me rephrase. The question was, why don't you take in old topologies as a starting point? And then, why don't you take in old topologies as a selection criteria, as a set of selections? And the thing here is, currently, topology optimization happens by operators manually doing things on the grid by their gut feeling. And gut feeling is probably good to a certain point, but our aim is really to find topologies that the operators did not think about. Because if the operators thought of a topology, they don't need a topology optimizer. They basically input a selection of topologies and choose one. That's pretty easy to do in a mixed integer setting. You just have a set of topologies, choose one, can pre-encode them. But the idea here is that we assume that what the operators do currently is not optimal. That their actions on the grid, they might be stable, they are safe, but they are not optimal. And the idea this is we don't want to take in any constraints based on historic actions, based on like imitating the behavior of the operators, because this would constrain us to the set of seen topologies. It's very convenient to get a topology optimizer to run with that set of pre-existing topologies, but then you will never see something which is beyond what has been done in topology. So the belief here is we have unused flexibility in the grid. There's more potential to change the grid than is actually being used. And maybe to this, there is actually, like, we found that there is quite a bit of potential just in rough numbers. If we only look at opening of busbar couplers, we can shave off like 5%, sometimes 10% of the total redispatch volume. But if we combine that with busbar reassign, we get numbers up to like 30% of reductions. And this is both good and bad. The bad thing is this is what drives combinatorial complexity. And it's also good because, well, it's a very high number. And then we had a really interesting phenomenon. We offered to our optimizer to do transmission line switching, and he just rejected to do it. In between, intermediate states had transmission line switching, but the converged solution just tends to not have it. I think this is due to us only optimizing the highest voltage levels, where you can actually do most of the effect with busbar reassignment and busbar couplers, and the reduction in meshedness, like the reduction in capacity you incur by taking out a branch, is actually not worth it if you can solve the problem with these two combinations. This might though change when we look at lower voltage levels, where sometimes like taking out a trafo or taking out a line in the lower voltage levels might be beneficial. So that's a bit of a question mark there. Also, I mean, we did quite some gambles. We did the gamble of taking DC, and it just works out great. So we find topologies that are looking good in DC, and then they also look good in AC, which is like not per definition the case. So this, we're just lucky, I guess. But in general, the usage of DC in the realm of congestion optimization is like quite prevalent. You see, for example, many OPFs in the congestion processes running on DC, just because congestion can quite reliably be solved in DC, and it still looks good in AC. And maybe also something I talked about, the amount of open couplers. We call it the simultaneous bus splits for us. You have a sort of diminishing return scenario that you incur more instability, but at some point you actually can't really scrape off more. So we have a situation here like a trade-off. The more we open couplers, the more we can reduce the overload, but also we introduce more instability. So then it's up to the operators basically to find a good trade-off there, how much instability can be introduced into the grid at any point in time. So yeah, it's an interesting multi-objective optimization problem even. And we have some things planned for the future, and with that I give back to Christian.
Thank you very much. Maybe just to clarify one thing. So everything we talked about here before was overload energy, so not redispatch cost, just to emphasize on this, because that's another topic to look at in another round. So what are we going to look at in the next, let's say in the next month? So as Nico already explained, some of the constraints have not been written down. They are from experience. So what we're currently trying to find out via different iterations, so if you've seen the different iterations where we're doing, to get this written down and somehow formalized that we can integrate this as our constraints. We are now in close contact with the grid operators. Some of them are here. And then, that's currently what we're going to look at to, on the one hand, have less asymmetric assignments, also look at short circuit currents, and also look at the switching distance. So basically, that you don't have to do too many switchings in a substation to actually release the work for the grid operators. Then we are also collaborating together with Tenet on this, and the idea is also to define general interfaces and modules for the whole topology optimization itself. So basically standardizing that in the long term we can also, or midterm even, exchange modules and also exchange what we do. So that's definitely ongoing. It also brings a bit of a legal topic to it, so this is why we need to ensure, and also with the long-term goal potentially of open sourcing this whole development. Next to this, we're also involved in graph neural networks for grid control, which is a research project, basically looking at graph neural networks for the load flow calculations. So this is one aspect, and the second aspect in there is to use then some kind of optimization among, for example, reinforcement learning to then potentially find a good topology. This is a 3-year project and will go until 26. And next to it also, you have seen already before, we looked at AC and DC, but of course there's also something in between. And one of the approaches that has been currently been tackling is to find a new way that is maybe a bit slower but more accurate, and we can also sensibly calculate voltage. And therefore, there is ongoing cooperation with Forschungszentrum Jülich that is going to publish an idea on how this could work in a theory. Also, some first tests have been done. So we're actually looking quite forward to this. Also with the goal for later to integrate also other problems, for example, to optimize also on voltage control at the same time. And this actually leads me to the last point, what's ongoing. So basically not only to look at topology optimization, but also then to optimize voltage next to it together holistically and potentially even add new topics to it. This is started this right now, so it's the first week on this, and it will go for 1 year, and is sponsored by the Belgium Energy Transition Fund. And as this is currently still an innovation project until the end of the year, next part will be that this will hopefully, and if we are successful, move into our module control center system. So this is an ongoing approach from 50 Hertz to modulize the control center. So basically the SCADA system as well on all kind of grid analysis topics on top. Yeah, and with this we conclude. We are open to share as much as possible. We do have some currently still ongoing constraints, but we are open to share it with all TSOs and also ongoing to open source it. We are attending some of the nice talks here earlier. And yeah, do you have questions? And with this, I finish and leave the room to you.
So first question here.
First, it is very nice talk, very impressive. I have a question. What about PSTs?
Phase shift transformers, yes. So phase shift transformers, there are two questions around phase shift transformers. For those of you in the room who don't know what phase shift transformers are, basically you can control the flow like a tap on a line with these things. And they are also non-costly. And usually right now they are optimized in a mixed integer fashion because you can very well linearize the phase effect. But there's also something called the PSDF, which goes into the like PTTF world. Right now we have outscoped that because this is already solved. But it would make much more sense to integrate this, so to optimize topology and phase shifters and HVDCs, and probably even more together. And that's why we start OptOmni, to look how we can integrate these things in the future, but we need to go one step at a time. So far, topology optimization isn't really solved, and probably it's not after our work as well, but we need to advance to a state where we can find good topologies on the fly that satisfy the constraints, before we go further. So basically what we did, we cut our scope a bit. It's a very good question. I don't think we will have we probably have like 50% more impact, or maybe even more if we look at phase shifters. We might have 50% impact or even more if we optimize on a larger grid and not just one. So for example, what we see right now, if we have time steps in Germany, where there's a lot of congestion in the D2 area, in the TenneT area, we can solve that congestion in the 50 Hertz area. So we can actually pull problems to the 50 Hertz grid, but the overall number of problems goes down. So there's a very high coupling between the grids. So there are questions in here. How can we advance this to be even more effective? But because we can only tackle one thing at a time, we tackle right now to make good topologies, like bus splits, bus bar reassignments, and transmission line switching. And actually for transmission line switching, we also mean phase, like transformers to turn them off. But yeah, it's a very good question. We should hopefully get there some point. But yeah, we're just 5 people as well, so. Okay, the next question back in the room.
So what is the time horizon that you are optimizing for? Is this a planning problem to discover new topology?
Yeah.
And if so, then I guess computational time, yes, is a bottleneck, but did you try and benchmark your optimum to that of a mixed integer?
So, question rephrased. What is the time horizon that we're looking at? And there are different time horizons in the grid optimization process where you can do topology optimization, starting from grid planning all the way to real time. Basically, the further down the line you go, the more time constraints you have. And currently, we settled on the day ahead operational planning. So we're not in grid planning, that we would have infinite time, but we want to go actually to day ahead operational planning, because this day ahead process, that's where these numbers come from mostly. So in grid planning, that's a very nice separate idea, that we could extend this idea. I mean, if you look at grid planning from a bird's eye view, it's basically a topology optimization, just that you don't remove lines and you don't split bus. What you do is you add lines, you increase the capacity on lines, you add equipment to the grid, like all sorts of things. So from a bird's eye view, it's a topology optimization, and we believe that the same idea that we did on topology optimization for congestion can be applied to the process of grid planning. That you take these mathematical ideas, which are very convenient, that you can compute a lot of things in very small incremental updates, put that on GPUs or some other sorts of accelerators, and massively brute force this problem of grid planning to just explore a lot of the space. Again, something which we unfortunately need to outscope because we're just a small team. But it's a very, very good idea to look at that as well and see if we can take this idea of we can compute a lot of load flows and apply this to grid planning.
You have it on grid code. So you just need to plug your magic DC into what grid code has already, and that's it?
Advertisement for grid call, we just need to plug the DC solver into grid call and it will work. So we should stay in contact.
It is the right idea. You know, the genetic algorithm is the right idea for these things.
Yeah. Other question back there.
Do you optimize preventively the topology or also post-contingently?
Okay, question was if we optimize preventative or also curatively. Currently, we're looking at preventative only. Basically, the difference, for those of you who don't know what the difference is, preventative actions are actions that you take no matter what happens, and curative actions that you look at individual contingency cases, and if there are actions that you can take quickly, for example, opening a coupler just in time, then the operators can put a rule set or just react quick enough to a contingency so that they don't need to implement that in advance. Again, it would make a lot of sense to separate between that at the point when we have topologies that satisfy the constraints. One of the other things, like, it's nice how this room basically reads our backlog. So we have a backlog on our Kanban board, and by now you've like guessed half of the tasks there. Yeah? We have two modes. We have a hard time coupling and no time coupling at all. So either we hard couple time steps, meaning it's the same topology for all of them, or we have no time coupling at all, meaning the topology optimizer starts from 0 again and finds topology out of the scratch. Again, you guessed another thing. This is actually not on our backlog. This is in the sprint to introduce something in between. So to say you start on one time step from scratch, but then you go to the other time steps with as minimal changes as possible. We also thought of optimizing it together, basically multiplying our problem by 24. But if this sequential optimization works, then probably that's easier than just multiplying it by 24. So hopefully that will work. Another, yeah?
Maybe I should have started like that. Very impressive. So, did you really implement the full DC, security constant DC security analysis on the from scratch?
Yes, so
Very implementation and everything?
So yes, we do a full n-1 analysis. We can outage branches via the LODF formulation. We can outage generators via the PTDF, just as the delta P. We can outage three winding chafers with the MODF formulation. And we can also outage bus also via the MODF formulation and PTDF formulation combined. So yes, we have implemented a full n-1 analysis. And for every individual topology, we actually compute a full n-1 analysis. And because it's fast enough, we don't even need to really throw out n-1 cases. We can compute them all. So for every load flow, we basically multiply our computation time by 2,000 to 3,000, computing all n-1 constraints which are computed in operation. Yes, maybe do you want to comment a little bit on that?
Yeah, basically, I think our team is quite convinced to open source this, and I think also some others. It's just that there are others people in the company that needs to also convince that we can move in general with this way forward. We're working on this also actively. Also, some colleagues are here in the room. So yes, I really hope that we get there soon. And as I said, we can already share certain of this among TSOs, because I mean the issue is that we already have been collaborating with Tenet, so also part of this will depend on Tenet if they are willing to open source, because for example for this DC load flow solver, part of them have they developed, part of us the GPU implementation we have developed and John have been together, so this needs to be aligned. But yeah, that's the current state, but I'm confident that we get there.
Okay, so we have 3 more minutes. Are there more questions? Okay, then maybe another thing, like looking at this GPU part, I believe we can also get AC load flows on the GPU. Probably not as impressive, but maybe we can create like an ecosystem of GPU-based solvers and software to speed up various processes. I mean, already the DC solvers, they can be used in multiple places, but yeah. Just a bit of vision.